So before we get started, I'm going to show a couple of slides and then we'll start into this ligand-gated channel story. But while I'm here, one of the things I think you should do, it's something I wrote several years ago, and I think it's worth looking at, because so many students get tangled in this change in concentration that people think has to happen for an action potential. I wrote something up a couple of years ago. I think I entitled "Why I Hate the Pump." And what it's a description of is a description of how the ions are flowing and how few ions it really takes to cause a depolarization. And if you like numbers, it actually goes through a quantification of that story. And the other piece to it is, if you can look at it and read it and understand it, you'll recognize that the action potential is not changing concentrations across the membrane very much. And in that write-up, and I think it's under the section of additional information, in that write-up, it also compares something known as sodium-potassium pump, which we mentioned in passing, as a charger for a battery. And the analogy that I'll commonly use is that the sodium-potassium pump is like the charger on your phone battery. And it's certainly true that you need to charge your phone battery every now and again to send texts from your phone. But you also know full well you can send an awful lot of texts before you have to recharge that battery. And the analogy here is that each text that you send is like an action potential. And the neuron also can send many, many signals, many, many action potentials without recharging the battery. And the recharging the battery is the sodium-potassium pump. So let me show you a couple slides, partly because I like these slides. This first slide shows an image of a neuromuscular synapse, and we'll come back to this when we talk about muscle here next week. But it's the same kind of structure that Langley saw when he was looking at individual mouse fibers. And when you look at it on end, you can see the motor axon, you can see these little boutons, these little bubbles, and these are all part of the axon, and this is now sitting on the muscle fiber. And this is sort of a face-on view looking at the extent of these axon terminals as they sit on the muscle fiber. And if we cut a section through one of these bubbles, one of those boutons, we see something like this. Now this is blown up a whole lot. To give you some idea of the dimensions here, these are the synaptic vesicles back here. These synaptic vesicles are about 30 nanometers in diameter. Then if you compare the diameter of these vesicles to the width of the synaptic cleft, this is about 50 nanometers. So what we're looking at here is the plasma membrane of the axon terminal, and what we're looking at here is the plasma membrane of the postsynaptic cell. So this is a real picture of what I'm going to draw on the board in a moment. We'll blow it up farther than this because we're going to look at individual receptors on this membrane, but this membrane is actually packed very tightly with transmembrane proteins that are the neurotransmitter receptors for the neurotransmitter that has been packaged in these vesicles. If we look closely here, there's a little bump, and this little bump is probably representing the calcium channels to the active zone. So we think the calcium comes in at this site, binds the synaptotagmin, triggers the winding together of the T snares and V snares, and this vesicle then will fuse the plasma membrane, and about 5,000 molecules of neurotransmitter then will come pouring out of this vesicle into this narrow gap. That neurotransmitter will diffuse very rapidly across that narrow space and bind to the receptors on the postsynaptic side. And that's what we're going to talk about now, the binding of the receptors to the postsynaptic side and what that generates. But before we do that, this is just a fancy picture of what I drew on the board. Again, in gray here, this is the VAMP or synaptobrevin. This structure up here is a tag structure, is synaptotagmin. This is syntaxin, which is the transmembrane protein in the phospholipid bilayer of the plasma membrane, and SNAP25 is this molecule, and this squiggle here is representing how the SNAP25 is tied in to the plasma membrane, but is not a proper transmembrane protein. And when the calcium binds to the synaptotagmin, these proteins all wind together, and they wind together, they shorten the distance between this yellow structure of, this phospholipid bilayer here and this phospholipid bilayer here and smush the two of them together. This next slide, this is a pretty picture, but it's worth spending a moment on. What it's trying to demonstrate is that this structure here is the postsynaptic cell. And this would be a synapse in the central nervous system. In contrast to the one I just showed you that was in the peripheral nervous system, this would be a synapse in the central nervous system. Now, up here, we're looking at these green structures being the synaptic vesicles clustered against the membrane. And this is the space in between would be the synaptic cleft. So all of this is a pretty picture, and all of this is fairly accurate. But what this really misses is that if we were to actually look at this in the central nervous system, that these synapses would be packed in here one next to another. You wouldn't see these vast stretches of empty postsynaptic membrane. You would just have all of these sort of extensions, all of these just chock-a-block full of synaptic sites. So there'd be thousands and thousands of these. So now what we want to do is we want to think about what's going on here. At a typical synapse that I showed you with the neuromuscular synapse, there will be about 5,000 molecules of neurotransmitter released, and that will open about 2,500 of these ligand-gated channels. The central nervous system is a little different. The central nervous system will still release about 5,000 molecules of neurotransmitter, but we may have no more than maybe 400 or 500 of these receptor molecules. Then when the receptor molecules bind to the neurotransmitter and the channel opens, sodium comes in. That influx of sodium through these so-called ligand-gated ionotropic channels, that influx of sodium depolarizes the membrane at this site. It produces a depolarization. Now let's look at this in context with our pineapple neuron. I'm going to have to, let me redraw that with the colors I have above. So the input region here So this is all input region. And the structure we have above would be located out here someplace on the input region of the dendrites. There would be hundreds of these, thousands of these. Each one of these is meant to be a synapse. And each one of these sites is composed both of the presynaptic element and the postsynaptic element. And what I mean by that is there will be vesicles in here, there will release neurotransmitter, and there will be these ligand-gated channels. These are intended, again, to be the ligand-gated channels. When the 5,000 molecules of neurotransmitter, one of those vesicles is released at this site, it opens a few hundred of these receptor molecules. The few hundred receptor molecules, each one allow some thousand or a few thousand ions of sodium in to depolarize the membrane. So that if we look at this site, we can imagine that we have generated here a potential that goes from minus 70 millivolts up to maybe minus 69.5 millivolts. So this is a way of saying that the opening of the ligand-gated channels produces a local depolarization at this immediate site of about half a millivolt, not much. But what's more now, remember that we have very few voltage-gated channels out here. that the postsynaptic membrane, this black membrane, has very little in the way of voltage-gated channels, but instead the voltage-gated channels are clustered here initially at this site called the trigger zone. These are the voltage-gated channels at the trigger zone. In some cases, particularly motor neurons, these synaptic sites may be a millimeter or more away from the trigger zone. And this input region is characterized by channels that we talked about before. Remember, we always have to have leak channels, so there are leak channels in here. Those leak channels are essential for establishing and maintaining the membrane potential. So these are leak channels. So now imagine that first image that we had yesterday, that long tube, where we started an action potential at one point and saw how that decayed over distance. Remember, it decayed over distance because there were no voltage-gated channels to reset or regenerate that potential. And again, out here in the input region, we don't have any voltage-gated channels. So what do you think is going to happen to the amplitude of this potential, this, I should label it. What do you think is going to happen to the amplitude of this excitatory postsynaptic potential as it propagates along the membrane? It's going to get smaller and smaller and smaller, such that by the time this depolarization reaches this site, even though it started out here as a half a millivolt, by the time it reaches this site, it may be no more than in the neighborhood of 0.1 millivolts. You'll remember at the trigger zone that in order to fire an action potential, the membrane potential has to be depolarized from about minus 70 millivolts up to at least minus 55 before we reach threshold, so that we can simultaneously open all the voltage-gated sodium channels. Well, if this is only a half a millivolt, or if this is only a tenth of a millivolt, that means, and we need a 15 millivolt excursion to bring the membrane potential to threshold, that means there are going to have to be 150 of these to fire an action potential. So this means, what this is telling us is that the release of neurotransmitter from a vesicle at an individual site is woefully inadequate to supply enough positive charge at the trigger zone to open voltage-gated channels. It means that to get enough positive charge at the trigger zone to open the voltage-gated channels, we have to simultaneously activate as many as 150, maybe more, of these synaptic sites. We need to have something like 150 or so of these postsynaptic potentials propagating along the membrane and arriving synchronized in time at the trigger zone. So a couple of things about this. First, let me see if I can spell it out up here. The neurotransmitter in each vesicle generates a small depolarization. It becomes even smaller. That decreases in amplitude as it propagates across the input region. I should say across the membrane of the input region. So this potential is getting smaller and smaller. And it's getting smaller and smaller because of the leak channels. Now there's an exercise I want to take us through to illustrate why these potentials are getting smaller. And this is a gross simplification, but I think for our purposes it'll work fairly well. And we're going to dwell here only on the membrane resistance. We're only going to dwell on how leaky that membrane is. So now think about that membrane in the input region as though it were the leaky garden hose, such that the more holes we have in the leaky garden hose, the less water we get out at the end. But here, to formalize this, I want to begin with a discussion of something called Ohm's law. This is a concept we'll run into in a number of places. We're going to introduce it here in terms of electricity. If you've had some physics background or if you're an electrical engineer, you'll recognize this straight away. What it says is that the voltage is equal to the resistance times the current. So this says voltage, I should actually say delta voltage, is equal to the resistance times the current. And the current you can really think of as the number of ions crossing the membrane. Now, the way we've described this is that we have a typical synaptic vesicle releasing its contents and opening a few hundred receptor molecules. They're more or less going to be the same. So that means we can think about the current as being more or less proportional to the number of open ligand-gated channels. The more neurotransmitter, the more channels that open, the greater the depolarization, the greater the current. If we fix this number, if we fix the resistance, we say the membrane resistance is a particular number, then we can see that the voltage will change with the number of ions moving. Simply put, the more ions that are coming in, the greater the potential. But this is an important term. This resistance term is important because if we could now change the membrane resistance, we'll have an effect on the amplitude of the potential. In other words, this is a term which describes the leakiness of the membrane. This is a term that describes how many of these purple leak channels we have in this membrane. So let's say in our initial story we have no leak channels. We can't have that because we need some leak channels. But let's take the extreme case where there are no pathways across which the potassium can leave. It's basically a perfect garden hose. Then in that case, the depolarization placed on the membrane here is going to fairly faithfully arrive at this site. But now let's increase the number of these potassium leak channels so that effectively what we're doing is we're reducing the value of this number. So now the resistance gets less because we've put more holes in the membrane. And so now because there are more holes in the membrane, more of the potassium leaks out, the more of the charge leaks out before it reaches the trigger zone. So the lower this number for a given current, the lower the voltage that's produced. The lower the voltage that's produced, the smaller this potential is arriving at the trigger zone. So now we can vary this over quite a large range, just in our thought experiment. If there are few leak channels, and this number is big, that tells us the voltage is going to be big. It's going to arrive fairly faithfully. If there are lots of leak channels, and this number now is small, then the voltage arriving at the trigger zone is going to be small. It's a simple characteristic of the membrane resistance. It's a simple characteristic of how many leak channels we have in that membrane. The more leak channels we have, the smaller the potential will be when it arrives here. The fewer leak channels we have, the fewer opportunities we have for the positive charge to leave, the larger the potential will be when it arrives at the trigger zone. So that means the membrane resistance is playing this really important role in determining how big these potentials are when they arrive there. But the fact remains that if we look at this site and we take a measurement, we measure the voltage, what we see at that site is that each time, for minus 70 millivolts, each time one of those EPSPs arrives, it produces a little depolarization in the membrane. And if they're in the right time frame, these guys will add together. Each one of them being perhaps less than a tenth of a millivolt. They add together, they can summate. This is said that the EPSPs, the excitatory postsynaptic potentials, summate. That's simply a fancy way of saying the voltage of each potential adds with the others. Now it's true, and I'll come back to this in a little bit, but it's true that there's this potential like this and it decays back, and then we wait and see another one. Those two can't interact. They're too far apart in time. The only time they can interact is when they arrive at the trigger zone more or less within, 10 milliseconds of one another, because the duration of these potentials is about 10 milliseconds. So these guys are adding together. And if we get enough of them to add together and they reach the minus 55 threshold, then we'll fire an action potential. But that decision is being made here at the trigger zone. And the decision is being made based upon the number of these excitatory postsynaptic potentials that are arriving coordinated in time at the trigger zone. If you don't have enough charge arriving from all of this synaptic input to bring the membrane to threshold, you'll never fire an action potential. So the decision as to whether or not to fire an action potential and signal the next cell is made here at the trigger zone by determining the degree of depolarization. So the amount of depolarization arriving at the trigger zone from these excitatory postsynaptic potentials adding or summating together will make the decision of whether or not there's enough positive charge to trigger an action potential. So any questions on that? Yes?
Is the action potential, or is at the trigger zone when the voltage summates, is that like action potential, I guess? Is that one, what I'm looking for? All or nothing?
So which part of this is all or nothing? That's a really good question. So these individual synaptic events, we can say that the amplitude of these individual events varies with the number of ligand-gated channels that are open. The more ligand-gated channels are open out here in the input region, the bigger these potentials. So they're graded. So they're said to be graded with the number of neurotransmitter molecules that open the channels. There's also a gradation depending on how much we've lost across the lead channels. But that's variable. But now once we reach this site, we now have an on or off question. Do we get enough positive charge from all of these individual synaptic sites bringing sufficient positive charge to fire an action potential? If we do, that's all or none. Action potentials are all or none. They go or they don't. If you reach threshold, you have an action potential. If you don't reach threshold, you don't have an action potential. So all of these tiny synaptic events, all these tiny EPSPs, are capable of summating or adding together. But at this point, the all or none signal is initiated depending upon how much positive charge is delivered to that site. So that's the distinction. You're absolutely right. There's a distinction that everything on the input region, because these are all ligand-gated inotropic channels, passive membrane, no voltage-gated channels, those are all graded with the number of ligand-gated channels that have been opened. But once we reach here, we either have sufficient positive charge laid on the membrane by all these EPSPs to bring the membrane to threshold, or we don't. If we have enough positive charge to bring it to threshold, then we have the all or nothing action potential.
So the EPSPs are in the input area, those are graded, and then at the trigger zone there's an action potential, which is stereotyped.
Exactly. So all of these inputs here that are the synaptic potentials, these are all graded. And the signal that's generated here at the trigger zone is all or nothing, and that's an action potential. So EPSPs are graded, and action potentials are all or none. Anything else? Yeah. So the question here is, well, what happens if we simply don't have enough charge reaching this site to cause an action potential? Well, nothing happens. This is a decision point. And some people who have a background in analog and digital think about it this way. They think about the input coming in over this membrane as all being analog, because you can add it all together in sort of some analog fashion. But at this point, at the trigger zone, it's either on or it's off. It's a 0 or a 1. Either you have it or you don't. So this is truly a kind of digital signal. But all of this in the input region is graded over a broad range, so it's analog. For some people that helps. Other people, if it confuses you, let it go. But the point is, these potentials are graded and can be variable over a broad range. Once we get enough positive charge at the trigger zone and open those voltage-gated channels to fire an action potential, that's a stereotyped all or nothing, always the same kind of signal, on or off. Okay? Anything else? Well, we've described here this idea of the membrane resistance. We've described the idea of EPSPs. Now, I'm just going to make a list here. And this is an obligatory list. And it's simply going to be a list of the small molecule neurotransmitters in the central nervous system. So I'll take this panel here, this portion of this panel, and fundamentally draw a box and simply label it as small molecule neurotransmitters in the central nervous system. These are small molecule neurotransmitters. In the central nervous system that open ligand-gated ionotropic channels. And it's a fairly small list. By far and away, the most common, probably 80 to 90% of the neurotransmitter molecules in the central nervous system that are opening these ligand-gated channels are simply the amino acid glutamate, sometimes called glutamic acid. This is the most common of all of the neurotransmitters. The next common neurotransmitter is one called acetylcholine. This is the same molecule that Löwy described as Wegestoff. It's also in the central nervous system. It's also an important neurotransmitter that opens these ligand-gated ionotropic channels. A third one, which is not nearly as common, is serotonin. These are a particular type called the 5-HT3 receptors. It's a subtype. Don't worry about it. And then finally, there's a fourth one here called gamma amino butyric acid. We abbreviate gamma aminobutyric acid as GABA, gamma aminobutyric acid. Now all of these, the glutamate, acetylcholine, and serotonin, all of these on ligand-gated ionotropic channels in the vertebrate central nervous system, all of these are cation channels. This one's different. GABA turns out to be an anion channel. The binding of the neurotransmitter GABA to the ligand-gated ionotropic channel opens the channel and increases permeability to chloride. So it's a chloride channel, it's an anion channel. The rest of these are cation channels. Now, having said that, well, that's something else in truth in advertising I have to point out, is in addition to these ligand-gated ionotropic channels, there are also a series of G protein coupled receptors, just like the ones we saw in the endocrine system. The G protein coupled receptors, the neurotransmitters for these will include particularly catecholamines. This will be norepinephrine, it'll be epinephrine, it'll be dopamine, it'll be this whole class of these catecholamines. They all work through G protein coupled receptors. By far and away, the most common of the serotonin receptors are not these ligand-gated ionotropic channels, but are GPCRs. And if you take another course in neurophysiology, you'll find that even all of these neurotransmitters will work through G protein coupled receptors. Again, an excellent example of how it's not nearly as important what neurotransmitter you have as what receptor to which that neurotransmitter binds. It's the receptor that determines what's going to happen, not so much the neurotransmitter. Sure enough, you have to have the right neurotransmitter with the right receptor, but glutamate can do a whole bunch of different things depending upon its receptor. So that's the obligatory list of the most common of the neurotransmitters. And now we're going to basically generalize to talking about, regardless of which of these neurotransmitters we're dealing with, that each one we're going to think about as an ionotropic channel generating an EPSP. That's what we've done for that model system. That's what we've talked about up here. I'm going to erase this now, and I'm going to replace it with the same pattern. And I'm going to put onto the input region a whole series of these excitatory synapses. But in addition to the excitatory synapses now, I'm going to intersperse among those excitatory synapses a series of inhibitory synapses. So what we're going to do next is we're going to place on this input region a series of synapses where the neurotransmitter is going to be GABA, and that GABA now is going to open a ligand-gated channel, but now the ligand-gated channel is going to be permeable to chloride. And we're going to walk our way through this first, just describing what those GABA-operated channels will do and how they'll change the membrane potential and how they'll change the membrane resistance. So let's take this region of the panel and describe the effects of chloride channel opening on membrane potential. And membrane resistance. So here's meant to be, I'm going to put it in black. Here's meant to be the input region of the postsynaptic cell. So simply what we had on the board before. Now, rather than emphasizing those blue synapses I had before, I'm going to put these in red. And then we're going to blow this up, and we're going to go through a similar exercise that we did just a moment ago. So this is intended to represent an inhibitory synapse. And if we talk about the inhibitory synapses as we did before, and we say this is the output region of an inhibitory synapse. When we look at it morphologically, it looks like any other synapse, and that means that we're going to have all of these synaptic vesicles back here in the cytoplasm. And we'll recognize that some of these synaptic vesicles are clustered up against the membrane. And then again, these synaptic vesicles reside docked against the membrane, immediately next door to the voltage-gated calcium channels. And in fact, the entire story that we went through earlier is true here. When an action potential arrives at this site, it provides a depolarization that opens the voltage-gated calcium channel. The calcium comes in, binds to synaptotagmin, same molecule, winds together those alpha helical regions of the T snares and V snares, and the vesicle fuses with the plasma membrane to release the contents. But now the contents are the neurotransmitter gamma amino butyric acid. Now, for the chemists among you, gamma-aminobutyric acid is simply a derivative of glutamate. And if you write out the structure of glutamate, the way we generate gamma-aminobutyric acid is to simply clip off the carboxylic acid group from the amino acid. And we clip that off, we now have gamma-aminobutyric acid. That's the detail of the chemistry. What we want to think about, though, is what happens when these molecules are released in the synaptic cleft between the output region of the inhibitory neuron and the input region here of the postsynaptic cell. Pretty much everything we've talked about occurs again. That is, there are these transmembrane proteins. They're in fact evolutionarily related to the acetylcholine receptor proteins. But now when the molecules of GABA bind to these receptors, and just as the molecules of glutamate open a channel, these too will open a channel. When the channel is open, though, the open channel now will allow for chloride to flow in. So this is representing an influx of chloride. So what do you think is going to happen to the membrane potential with that chloride, if the chloride's flowing in? It's going to make the membrane potential, what's the charge on the chloride? What's it going to make how is it going to affect the membrane potential in here? Let's make it more negative. So if we'd plot this, we'd see that if we start out at minus 70 millivolts, and if at this point we open these ligand-gated channels and chloride comes in, we'll get what's known as a hyperpolarization. this hyperpolarization now results because of the influx of chloride. Where this hyperpolarization reaches, however, is dependent upon the equilibrium potential for chloride. Remember, each of these ions will have its own equilibrium potential. So if we open these chloride permeable channels, and the equilibrium potential for chloride in this particular case is, pick a number, say minus 72 millivolts. Then if the resting membrane potential is at minus 70, and we open those channels, we're going to drive the membrane potential toward the equilibrium potential for chloride. It's the mantra again. The membrane potential seeks the equilibrium potential for the ion whose permeability is dominant, and so we'll drive that membrane potential toward the equilibrium potential for chloride, and it's easy to see that's hyperpolarizing. Well, what happens if E sub Cl is not, say, 72, but let's say E sub Cl is equal to minus 70 millivolts, the same potential as the resting membrane potential? What if then we open the chloride channels, we increase the permeability to chloride, what's going to happen to the membrane potential here? The membrane potential seeks the equilibrium potential. The ion whose permeability is dominant. What's the equilibrium potential? What did we just say? 70, minus 70. So are we going to see any change in the membrane potential here? It won't change. It's stuck right here. Now, and this happens often in biology, now let's take the case where the equilibrium potential for chloride is not minus 70, but pick a number, minus 65 millivolts. So the equilibrium potential for chloride is more positive than the resting membrane potential. So what happens if we open the chloride channels? Membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. So this membrane potential is now going to depolarize toward minus 65 millivolts. And at this point, most students say, wait a minute, whoa. I mean, you've told me depolarization is always excitatory. And now you're telling me there's an inhibitory neurotransmitter that's inhibitory that's in fact depolarizing the membrane. Both are true. And the reason they're both true is that what will happen, even if we depolarize the membrane potential from minus 70 to minus 65 millivolts, that as long as the dominant permeability is for chloride, even as we try to increase more sodium permeability, as long as the dominant permeability for chloride is for chloride, we're going to be stuck. We're going to be clamped at minus 65 millivolts. So that's inhibitory. We cannot move the membrane potential any closer to threshold because we've effectively clamped the membrane potential at the equilibrium of chloride. That's why it's still inhibitory. So do you all follow that? Because we're going to take it one step farther here. Okay, if that's all clear, remember, and I'll put these in green, that we have across the membrane here at these inhibitory synaptic sites, we now have these chloride channels. Now, from the point of view of the cell, it doesn't really matter from the point of view of the cell whether chloride comes in or potassium leaves. So now we can think about these chloride channels in much the same way we thought about the potassium leak channels. And remember what we said about the potassium leak channels. We said let me do it this way, the greater the number. I gotta go soon. Okay, the greater the number, of leak channels, the lower the membrane resistance, R sub n. So the more potassium leak channels we add, the lower the membrane resistance. But now we have chloride channels that can effectively do the same thing. So what is opening the chloride channels going to do to the membrane resistance? It's going to lower it. What's that going to do to the amplitude of the EPSPs as they propagate across this membrane, which basically has holes in it? It's going to lower it. So that means inhibition is going to reduce the amplitude of the potentials that arrive at the trigger zone. And in this way, now we can regulate the amplitude of the EPSPs reaching the trigger zone and regulate whether or not that generates an action potential. Let's leave it there. Think about that over the weekend, because there's a lot to unpack there, and we'll come back to this on Monday.